Imagine a thief who wants to rob a house. He has a backpack with a maximum weight capacity. Let's say the weight capacity of the backpack is 5 units. When the thief enters the house, he finds several valuable items. Each item has some associated value and weight. Let's say there were four valuable items: a gold bar, a silver bar, jewelry, and a diamond. Weight of the gold bar is 5 units and the value is 7. Weight of the silver bar is 3 units and the value is 4. Weight of the jewelry is 4 units and the value is 5. Weight of the diamond is 1 unit and the value is 3. Now we try to understand the problem that the thief is facing. Thief cannot keep all items in the backpack because the backpack has a fixed capacity and the sum of weights of all items is greater than the capacity. Thief needs to be smart while keeping the items in the backpack. If the thief keeps the item with the largest weight, which is the gold bar, the backpack will be full and value that the thief will get from the backpack is 7. But what if the thief keeps the jewelry and the diamond? Then the value of the backpack will be 8. Here the thief has explored two options. In one, the value of the kept items in the backpack is 7. In the other, the value of the kept item in the backpack is 8. You might be thinking, what is the issue in this? Anyone can find the best option for the thief. But now think again. In the considered case of the thief, there are only 4 items. That is why doing the calculation is easy. But what if there is a large number of items? Suppose the thief comes to us. The thief has a backpack with a fixed capacity and n items. The thief gives this problem to us and we have to find the best option for the thief. For the time being, assume that we have a solution in mind, but how are we going to represent the solution so that the thief can easily complete his job? Here is the idea. We have to tell in the solution which item the thief has to keep in his backpack and which has to leave, right? So there are two possibilities for each item. We can keep an item in the backpack or we can leave the item. Let's represent leaving the item with 0 and keeping the item with 1 for an item. If there are n items, there will be such n representations for n items. For example, if there are 6 items, which means n equals to 6, then we have a string of ones and zeros of length 6. For this video, we considered the case of the thief with 4 items to explain the knapsack problem. Let's say we designed a solution, but how the thief is going to know which digit is representing which item? Therefore, we need to keep items in a fixed order that will be known to the thief and us. Here, for the time being, we assume that after receiving the item, we will sort them in ascending order of weight, and the thief and we both are aware about this. So to design a solution, we sort them in ascending order of weight. Now we design a solution for this problem. When we write 0101, it means the thief must keep the silver bar and the gold bar because associated digits are 1, and the thief must leave the diamond and the jewelry because associated digits are 0. I hope now you get the point that order needs to be fixed so that we can design the solution and a thief can read our solution. The order that we agreed on is that items will be sorted in ascending order of weight. Now consider each digit, which can be either 0 or 1, and the number of items is 4. A solution is a binary string of length 4. There are such 16 binary strings possible. But the most important question is how we get the solution that gives maximum value considering the limitation of weight capacity of the backpack. We have to explore all possible solutions to find the best one. One possibility is we can keep all items in the backpack. The solution will be 1111. But can we keep all items in the backpack? Answer is no, because it exceeds the weight capacity of the backpack. What if we keep the diamond and the silver bar? The sum of the weight of the diamond and the silver bar is 4, which is less than the capacity of the backpack. So there are two types of solutions. One that satisfies the constraint of weight capacity of the backpack, we call it a feasible solution. The other that does not satisfy the constraint of weight capacity of the backpack. We call it a non-feasible solution because it exceeds the weight capacity of the backpack. We will get the best solution among feasible solutions. When we generate a solution, we have to evaluate two things. If the solution is a non-feasible solution, we will not consider it. If the solution is a feasible solution, we will consider it and calculate the value of the solution, that is, the sum of the value of the items which has an associated digit 1. We will store this value so that we can compare it with other feasible solutions. Now we are going to explore all 16 solutions. We will start with the first possible solution. We do not keep any item in the backpack. In this case, the sum of the weights of the items kept in the backpack is 0 and the value of the backpack is 0. We design the next solution. We keep only the gold bar in the backpack. In this case, the sum of the weights of the items kept in the backpack is 5 and the value of the backpack is 7. Similarly, in the next solution, we are keeping only jewelry in the backpack. In the next one, we are keeping jewelry and the gold bar in the backpack. Similarly, all other possible solutions are created. Now we will check which solution is feasible and which is non-feasible. Let's start with the first one. Here, the sum of the weights of the items kept in the backpack is 0, which is less than the weight capacity of the backpack, that is 5. Therefore, the solution is feasible. Let's explore the next one. Here, the sum of the weights of the items kept in the backpack is 5, which is less than or equal to the weight capacity of the backpack. Therefore, the solution is feasible. Let's explore the next one. It is also a feasible solution. Next one is not a feasible solution. The sum of the weights of the items kept in the backpack is 9, which is greater than the weight capacity of the backpack. Similarly, we observe the remaining solutions. This one is a feasible solution. This one is a non-feasible solution. This one is also a non-feasible solution. This one is also a non-feasible solution. This is a feasible solution. This is again a non-feasible solution. This is a feasible solution. This is a non-feasible solution. This is a feasible solution. This is a non-feasible solution. This is also a non-feasible solution. And the last one is also a non-feasible solution. After exploring each possible solution, the best solution is when we keep the diamond and the jewelry in the knapsack. Let's change the problem and increase the capacity of the backpack to 9 units. Now, solutions which were feasible earlier will be feasible in this case also because we are increasing the capacity of the backpack. But a few non-feasible solutions will become feasible now. In this case, the best solution is when we keep diamond, silver bar, and the gold bar in the knapsack. Let's summarize the problem. We have n items. Each item has associated weight and value. We have a backpack, which we call knapsack in the case of the knapsack problem. Weight capacity of the backpack or the knapsack is fixed. The objective of the problem is to keep items in the backpack or the knapsack in such a way that sum of the value of the kept items is maximum and the sum of the weight of the kept items is less than or equal to the weight capacity of the backpack. In the case of n items, solutions can be represented by a binary string of ones and zeros. Each digit represents whether we are keeping the associated item in the backpack or leaving the item. Here, total possible solutions are to the power n. Among 2 to the power n, a few solutions may be feasible and a few solutions may be non-feasible ones. In the set of feasible solutions, we have to find the best solution. In this video, we explored what is knapsack problem. In the next video, we will explore why this 0-1 knapsack problem is considered hard to solve. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.